Hi, my name is Braden Marconi, and today I'm presenting Lab 4 on magnetic fields of a bar magnet. The goal of this lab was to experimentally analyze how a bar magnet's magnetic field behaves with distance and orientation compared to theoretical dipole behavior. From our results, we obtained a dipole moment of about 39.8 and a slope of negative 1.058 from our plots. Ideally, we expect a slope of -3 for a dipole, so this deviation already tells us there were some errors during the experiment. This experiment is based on the Biot-Savart law, which describes how current produces magnetic fields. A bar magnet behaves like a magnetic dipole, meaning its field depends strongly on direction. Along the axis of the magnet, the field is strongest and allows a specific inverse cubic relationship. While perpendicular to the axis, the field behaves differently in both magnitude and direction. The key parameter we're solving for is the magnetic dipole moment, which characterizes the strength of the magnet. We placed a magnet at the origin and used a magnetometer to measure the magnetic field at various distances. We took measurements both along the axis of the magnet and perpendicular to it. To reduce interference from Earth's magnetic field, we aligned the setup carefully before collecting data. We recorded magnetic field values at multiple distances and averaged them. To analyze the relationship, we plotted the natural log of B, magnetism, versus the natural log of R, the distance. We should produce a straight line if that field follows a power law. This allowed us to extract both the slope and constant K. We also measured the magnetic field off axes, specifically at positions perpendicular and at 45 degrees from the magnet. These measurements help test whether full vector dipole model matches reality, not just the simplified on-axis case. To compare theory with experiment, we built a computational model using the dipole magnetic field equation. This model calculates the magnetic field vector at any point in space based on the dipole moment. We then use this to predict what the field should be at the same position where we took measurements. Using our calculated dipole moment, the model predicted an off-axis field of approximately 1.34 times 10 to the -4th, in the x, 4.02 times 10 to the -4th in the y, and 0 in the z. This gives both magnitude and direction, which we can directly compare to our measured values. Observations. Our observed values did not perfectly match the theoretical predictions. The largest issue was that our slope was far from the expected -3, indicating that the field did not follow ideal dipole behavior in our measurement. This likely came from experimental errors and environmental magnetic fields, such as the other magnets in the room, phones, and all the other different kinds of technology in the area. Additionally, our sensors and the apps we used are quite limited in their precision. So what if? What if we hadn't aligned the experiment with the Earth's magnetic field? Our measurements would have been a combination of Earth's field and the magnet's field. That would make it impossible to separate the two, essentially ruining the data. If we instead use two identical magnets, the principle of superposition tells us the field would add, so we would expect all measured values to roughly double. And thank you for your time.